All right, so chapter 2.6, we're going to be talking about rational functions, and specifically their asymptotes is going to be kind of a major area of emphasis here. So a rational function is really any function that can be written as a fraction, a ratio of two polynomials. Throughout this, we're going to be calling the numerator polynomial n, the numerator, and the denominator polynomial d. For denominator. Again, these can be any degree polynomial for degree 0. They could just be a constant term like 1 or 2 or -6 or something. The only thing that they can't be is the denominator can't be 0. And obviously, if the numerator is 0, that's kind of silly too. So none of them will be just equal to 0. There'll be some sort of actual function involved with them. Another thing that we're going to assume as we go through this is that there are going to be no common factors between n and d, meaning that if we factored them, we couldn't cancel anything out. Otherwise, we're going to run into some issues here and there. So if they are factorable and we can simplify them out, we might want to do that before we start doing the other things. All right. So one thing that we can do with rational functions is establish the domain. What are the allowable inputs into this function? What x values are part of our domain? Now, with rational functions, the big thing is any x value that causes our denominator equal to 0. Those are going to be considered excluded values. So excluded values. So generally, we can set up an equation where we set our denominator equal to 0. And depending on the type of equation that we end up with, whether that's a first degree equation or a quadratic like this, we need to solve it appropriately. This one could be solved in a couple ways. This is a difference of squares, so we could solve it by factoring. We could solve it by adding 9 to both sides and then using the square root operation. A lot of options to us here. But depending on the equation, we need to solve it in whatever way is appropriate so that we get all solutions. Because any of the solutions to this equation need to be excluded from our domain. So I'm going to go ahead and solve this. I'm going to choose this approach. Feels like the easiest here. So I get x squared equals 9. Square root, we're going to get x is equal to plus or minus 3. So these are the values that need to be excluded from our domain. If we plug them in, they're going to cause our denominator to equal 0. It's pretty obvious when we just look at this. 3 squared minus 9, 9 minus 9 is 0. So I'm going to write the domain this way. The domain is all real numbers except x equals positive or negative 3. So this is going to be the way I write it. Pretty common way. There are some other ways that it could be written. We could just write it as x is not equal to plus or minus 3. I like it this way, though. Now, for rational functions, that's really it. We just need to figure out what the excluded values are, solve for them, identify them. Conveniently, that's actually the same exact method we're going to use to find vertical asymptotes. Vertical asymptotes are always going to occur when the denominator of our rational function is made into 0. I am struggling with the right screen. There we go. So anything that causes our denominator to equal 0 will be an asymptote. Now, what is an asymptote? So an asymptote is when our graph either approaches positive infinity, like this one is, it's going up to positive infinity as the x values approach a certain number. So as it approaches -1 in this case, or they could also go the other way. So as x approaches -1 this way, we can see our graph is approaching negative infinity. If our graph has this behavior, it grows without bound as it gets closer and closer to a particular x value. That is an asymptote. That is where there's an asymptote. And so it could either be on one side going down, the other side going up. They could both be going up. They could both be going down. All of those are representations of an asymptote, a vertical asymptote. So let's go ahead and just take a look at a couple asymptotes. when we graph these on Desmos, you're not going to see the asymptote actually graph. That's something that we will actually have to graph. So in this case, as it was approaching -1, this is the equation of the asymptote. And I'll even show you how we can kind of type that in and make it a dotted line to represent an asymptote. So here are a couple other examples of vertical asymptotes. Here's a function right here, and you can see at -2, right here we have a vertical asymptote. The graph is growing to positive infinity on both sides there. Here there's a couple vertical asymptotes, one at -4 and one at 2. It's approaching infinity, going down to negative infinity, down to negative infinity, up to infinity. It's having that asymptote behavior at those particular x values. And you can see those are the numbers that would make our denominator equal 0. So if I put a 2 in here, 0 times 6, this is 0. If I put a -4 in here, -4 is 0 times -6, yeah, 0. So it's undefined there, and the graph is growing, growing without bound, decreasing without bound at those particular x values. The next thing is horizontal asymptotes. So horizontal asymptotes are a little bit different. They are horizontal lines that as our function goes either down to it or up to it, as the graph goes either to positive infinity, like it is over here, or as the graph goes to negative infinity, as it's doing over here. So you can see on this side, as the graph is growing, as the graph is going to negative infinity on the left side, as the x values are going to negative infinity, it's approaching this particular horizontal line, y equals 2. Same is happening here. As we go out to positive infinity along the x-axis, it's approaching that line as well on this side. That is the behavior of a horizontal asymptote. Again, this line is not graphed for you. When we graph this on Desmos, we have to figure it out and plot it. There also appears to be a vertical asymptote in this case as well, but that's just for something else. Here are a couple more examples of some horizontal asymptotes. Here we have one that is along the x-axis at y equals 0. That would be the equation of that one. And here we have a horizontal asymptote at y equals 4. We'll talk about how we find these specific things in a moment, both the vertical asymptotes and the horizontal asymptotes. You can also see that this one would actually have a vertical asymptote at -5 as well, or this one would have one at 1. You can see it, yeah, you can see the behavior there. All right. Here are kind of the general rules for all of our asymptotes, both vertical and horizontal. So vertical asymptotes are at the zeros of the denominator. So when our denominator function equals 0, we have to solve that. Any solution to this equation is going to have a vertical asymptote, as long as these functions have no common factors. If there are common factors, we have to cancel those out first, then solve it. The next thing are horizontal asymptotes. There's always only going to be one at most one. And these are the 3 conditions. We have to kind of remember these, or at least be able to look them up quickly. So it has to do with the degree of the numerator and the degree of the denominator. So the highest exponent power. So in the first case, if the degree of the numerator is less than the degree of the denominator, then we're going to have one at y equals 0 at the x-axis. If the degrees are equal, the degree of the top and the degree of the bottom are equal, then we have this kind of weird thing going on where it is a ratio of the leading coefficients. We can actually step back and look at a quick example of this in a moment. And then the last one, we have if the degree of the numerator is greater than the degree of the denominator, there will be no horizontal asymptote. In this case, in the next chapter, we're going to learn that there's actually another type of asymptote that we can have that are different. So there will be something in this case, just not a horizontal asymptote. So it'll be some other asymptote. Now, depending on the degree difference, there can be different types. Mostly we're going to focus on, in this next section, slanted asymptotes, but there can be others too. Let's go ahead and look back at an example of B here real quick, where the degrees are equal. Sorry. Yeah, I want to erase some of this. So the one I'm thinking of is this one right here. Let's just clear everything. Here we have a degree of 1. This is first power, and degree of 1 also. So the same degree on the top and the bottom. So it's going to be a ratio of the leading coefficients. So leading coefficient here is 4. Leading coefficient here is 1. 4 over 1. We get this asymptote at y equals 4. Pretty simple. Horizontal asymptotes are easy. We just have to remember the rules. All right. Find the zeros of the denominator. So finding the zeros of the denominator actually help us find two things. They find the vertical asymptotes, but also the domain, the excluded values for the domain. So useful in two ways. So we need to set up an equation here, and this is a quadratic equation. We have a few ways to solve quadratic equations. We could use the quadratic formula, or we could factor, or we could even do like completing the square or something. I believe this is factorable, so that's the way I'm going to go with this one. I need two numbers that multiply to -8 and add to -2. So that is going to be 2 and 4, and the 4 needs to be negative. Yeah. So that tells me this factors as x plus 2 times x minus 4. And then using our zero product property, what would make these 0? Or we could solve this equation. We can obviously see this is going to be -2. So there's one of our vertical asymptotes, or the one of the excluded values from the domain. And then this one here, same thing. We could set up this little equation using our zero product property. Obviously 4 is the solution here. Here is our other vertical asymptote. So if we were kind of sketching out the graph at -2, we would have a vertical asymptote. Usually they're drawn as dotted lines like this. And then at x equals 4, we'd have another one. Now, we haven't really talked about how we figure out what it looks like in the middle, but we know where the asymptotes are. Now, depending on what the denominator looks like, the solving could be really easy, or it could be a little bit harder, involve factoring like we just did, or it could be even harder if it's like a third-degree polynomial or something. All right. Let's go ahead and find these vertical asymptotes. All right. So same idea. What makes this equal to 0? That's where our vertical asymptotes are going to be. We would want to make sure there are no common factors here. In this case, I know there's not, but that's something to check. Generally, we assume that the numerator and denominator don't have any common factors when we're dealing with a rational function, but we know from like some previous work that there could be here, and we would want to cancel those out. All right, so we could solve this a couple different ways. We could either factor this using difference of squares factoring and solve it that way, or we could just add 9 to both sides, divide by 4, and take the square root. That actually seems like the fastest way, but this is difference of squares, and we could do it that way as well. That means it would factor as 2x minus 3 times 2x plus 3. That would be a factoring for this. But I'm going to go ahead and finish it this way. 4x squared equals 9, divided by 4. Get x squared equals 9 over 4. And then when we take the square root, square root of 9 is 3, square root of 4 is 2. So we get plus or minus 3 over 2. Those are our vertical asymptotes at positive 3 over 2 and negative 3 over 2. Next one we have right here. Again, a couple ways we could solve this. Actually, in this case, this is not difference of squares anymore, so it seems like the only way is kind of the same way I just did that one. Sorry. I will subtract 4 from both sides. I get x squared equals -4. And okay, when I take the square root here, I'm actually not going to get a real number anymore. I get x equals plus or minus 2I. So in this case, we had no real solutions to setting the denominator equal 0. So there's actually no vertical asymptotes in this case, because we can't have vertical asymptotes at imaginary numbers. Where would we put them on the graph? There's no imaginary numbers on our xy graph. So, oops. So we wouldn't have a vertical asymptote in this case. All right. Let's go ahead and look at the horizontal asymptotes. And I do have a little cheat sheet up here in the corner. If the degree of the numerator is less than the denominator, right there. If they're equal, that's what we do. If the numerator is greater, that's what we do. So a little cheat sheet just to help us. So on top here, we have a degree of 1. Degree 1. On the bottom, we have degree 2. So the degree of the numerator is less than the denominator. Right here, we're going to have a horizontal asymptote at y equals 0. We can check this one out here in a minute if we want to, but that's our horizontal asymptote. Here, the degree is equal. We have degree 2 on top and degree 2 on the bottom, exponent of 2, exponent of 2. So this one is the ratio of the leading coefficients, 3 over 1, which is y equals 3 for our horizontal asymptote. Pretty easy. We just need to remember these rules for horizontal asymptotes. And we didn't have an example of this, but we'll have plenty of those in the next section. All right. Some other important graph features, y-intercepts and x-intercepts. We'll want to make sure we plot those when we are graphing these rational functions. So we want to remember that this is actually useful for all functions in general, but y-intercepts will occur at x equals 0. X equals 0 is the y-axis. The y-axis occurs when the x-coordinate is 0. So all we have to do to ever find the y-intercept of any function is evaluate f of 0. That's what we do in this case too. X-intercepts are going to occur when the function output equals 0, so when the y value is 0. So that happens when the numerator equals 0. Because for a fraction, when 0 is on top and it doesn't matter what number's on the bottom, this is going to be 0. So whatever makes the numerator 0 is going to make the whole rational function equal to 0. So we have to set the numerator equal to 0. Similar when we're finding the vertical asymptotes. Just depends on what the, except for with the vertical asymptotes, we're working with the denominator. Okay, let's do an example of that. Okay, I feel like we've seen this function a couple times. So let's first figure out the y-intercept. Function should have only one y-intercept. Otherwise, they wouldn't pass the vertical line test. So f of 0 is going to be 2 times 0 plus 1, 4 times 0 squared minus 9. 2 times 0 is going to go away. 4 times 0 going to go away. We're going to get 1 over -9, or -1/9. So that's our y-intercept. Same idea over here. Let's go ahead and find our y-intercept. We'll do f of 0. It's going to be 0 squared plus 3 times 0 minus 40 over 2 times 0 plus 1. 0 squared plus 0, 0. We're going to get -40 over 1, which is just -40. Pretty easy to evaluate f of 0. Kind of showed that really quickly. Then we want to find the x-intercepts. Now, that kind of depends on what the numerator looks like. This one will be a little easier because this is a linear polynomial, first degree. What would make that equal 0 is a pretty easy equation to solve. Divide by 2, I get x equals -1/2. In this case, I had one x-intercept. On this one, a little more complicated. It's a quadratic, so I might want to factor that. Let's see. Two numbers that multiply to -40 and add to 3, 8 and 5, and the 5 is negative. Yep. So that's x plus 8, x minus 5, and we want to know what makes it equal 0. Well, x equals -8, x equals +5. These are our two x-intercepts for this one. It's not too difficult. You know, we've done a lot of work in this class, and you probably did last year, in solving different polynomials. So hopefully this part is not too troublesome right now. All right, I think we're going to try to put this all together and actually kind of glance at a couple graphs. Yeah, so let's go ahead and put this together. Let's identify the domain and the vertical asymptotes. Remember, that's more or less the same thing. We want to know what makes the denominator equal 0 for both of those. So kind of two birds with one stone here. This is a linear polynomial, so we can just solve this adding 2 to both sides, dividing by 3, we get 2/3. So we're going to have a vertical asymptote at 2/3, and our domain is going to be all real numbers except x equals 2/3, and our vertical asymptote is going to be x equals 2/3. Pretty easy there. Second step, identify any horizontal asymptotes. So here we have a second degree on top, x squared, and a first degree on the bottom. That is the last situation. Degree of the numerator is greater than the denominator. So that means there's actually no horizontal asymptotes. You may want to reference that list or that cheat sheet when you're trying to figure this one out, because you probably don't have that memorized yet. Done with that one. And now y-intercept. That's pretty easy. We're going to plug in 0 for all the x's. You can even sort of see what we're going to get, right? 0 plus 0 minus 5, 0 minus 2. So for our y-intercept, I'll just go ahead and plug it in. Three times 0 minus 2. This is 0, 0 minus 5, 0 minus 2. That is actually 5 over 2. Negative over negative turns to positive. Or 2.5, however you like to think about it. And then the last thing, we just did this. Last thing, find any zeros or x-intercepts. Okay, x-intercepts, that's when the numerator equals 0. X squared plus 4x minus 5 equals 0. Okay, factor this, we need two numbers that multiply to -5 and add to 4. +5, -1, x plus 5, x minus 1. Opposites of that are going to be our x-intercepts. So x equals -5, x equals 1. These are our x-intercepts. All that's going to go together to help us make a sketch of these graphs. Now, obviously, we can use Desmos to graph them, but understanding where they come from algebraically, also valid, also something I'm going to ask you to do. All right, we're going to go ahead and stop right there, and I'll see you guys in the second part, 2.7.